This talk's called Big Data Collection, Storage and Analytics. It was supposed to be an overview of any possible way of logging operations and business knowledge, transforming it in any possible way, aggregating, storing, and then using and visualizing it. And I realized if we did that, you'd spend the next day and the whole weekend with me here, and that's not really entertaining in the long term, because I run out of jokes at some point. So I cut it down a little bit, and it's going to be a very quick overview. We'll look at offline processing, or actually batch processing, Hadoop, and some of the newer real-time solutions for big data. Most of you will be interested in the batch processing problems, because I don't think there's anybody in the room running Twitter. If you are running Twitter, you already know all this, so go grab a coffee. I'm excited to be here, because for the first time ever in any talk, I have 2 laser pointers. That's cool. So, whilst I'm wrestling with my microphone, which it keeps falling down, my name is David. I am German, as you can tell from the umlaut. All non-Germans can spell it like this. I'm from Munich, where I work as the founder of a consulting company called BitExtender. We do various web architecture, consulting, scalability, big data things. I'm also the lead developer of the Agave framework, which shares old common ancestry with Symfony, actually. This is me on Twitter. And before we dive into looking at how to process big data, I'd like to look at what the challenge actually is about processing that much data, okay? Because everybody says, well, we have a big data problem now, but the question is, how much data do you actually want to process, right? If you look at, well, what others do with big data, and that's the real big players, Facebook, for instance, the amount of data they ingest in any form, be it clicks from users on the front end, sent messages, anything, grew from around 200 gigabytes a day in early 2008 over, and those are compressed numbers, it's always a bit inconsistent how they publish them, to, tada, the newest one is half a petabyte per day. That's a lot of disks, right? That gets expensive if you have floods in Thailand and stuff, and they all store this on spinning disks. So they can't store everything on SSD. Even Facebook would go broke then. And Google, they published some numbers back when the whole MapReduce and Hadoop thing was becoming fashionable in 2007. Back then, they were already processing 400 petabytes of data using a technique called MapReduce. And on average, their job size is 180 gigabytes. So if you have that much data, well, you don't, right? So what if, let's say, something more realistic. What if the 180 gigabytes Google processes in a single run is all the data you have? And now you want to look at all this data. It's maybe order summaries and everything you have, signups, etc., from a couple of years of running an online shop. 180 gigabytes sounds easy, right? That's not a problem. Well, the bad news is, if you just want to read that sequentially off a hard drive, it's going to take you 45 minutes. And then you haven't even done anything with it. And you can't keep everything in memory because you don't have that much memory, right? So you can't process everything at once. You need to somehow split it up. And the whole 45 minutes, 480 gigabytes, roughly, so this ballpark figure, leads us to a general rule of modern computers that's valid even with SSDs. SSDs just shift the problem by at most an order of magnitude. Computers can read data process data much faster than they can read it, right? You remember the olden days, even when you had old computers with floppy drives, and the floppy drive would go until you retry or abort, and then you press retry, and then at some point it works, and you would wait forever. Even your old shitty A386 or something was a lot faster than your floppy drive. So we somehow need system and architecture where we can parallelize our processing, right? But that means we now need to coordinate a bunch of things, which is really difficult, because how do you even avoid overloading your network, right? You keep adding nodes, and at some point even your gigabit Ethernet might get saturated. Or what happens if one of the nodes in your cluster dies, right? Do you lose any data? Do any of the other processes have to restart just because one of them failed? So how do you make that durable? How do you coordinate everything? Gets us to chapter 1, batch processing of big data. There's a bunch of solutions for batch processing. You can do it yourself with AWK and SED and just, move stuff around a network, aggregate all your logs from your 50 web servers on a single box. It takes a moment, and then you grab through it, and then you sort and unique it. But that doesn't work until, at some point it's just going to be too much for that single box. And there are other solutions, commercial big data tool sets. I'm going to ignore those, because Hadoop is now the industry standard for anything you want to do with batch processing. It's a really, really interesting and powerful stack of software, as we'll see later. And I wouldn't bother with anything else if you have that much data. So let's look at that in closer detail first. MapReduce is the underlying programming paradigm that you use when you use Hadoop, right? The idea is that you used to have the data distributed across a grid, like little instructions, little bits of data, and you would ship them around, or maybe even store the data centrally on a SAN or a NAS, which really worked for small workloads. Let's say molecule folding for cancer research. You guys know folding at home, right? Or SATI at home. We look for aliens somehow. That's fine, but because you download maybe 30 kilobytes, and then even with the help of your GPU, your computer probably spends 10 hours working on this bit of information, 30 kilobytes, right? So that was a different era when people would do climate simulations even and stuff with small samples of input data and really, really computing intensive tasks. So you'd have Beowulf clusters, etc. That's what the supercomputers at universities are good at. But nowadays we have big data, which gets us an I/O bottleneck. Because if you have 500 petabytes, terabytes coming in a day, then you really quickly need a solution where you don't send all the data around the network. So Google figured that problem out really quickly, because they are a search engine and everybody Googles everything, right? Unless you use Bing, then you Google with Bing. But so in 2004, they published a paper called Simplified Data Processing on Large Clusters. And the idea is that we now distribute our data in some way. And then we compute the data on those nodes where the data already lives. So you have basically a massive distributed file system, and on this distributed file system, you have redundant storage even, so your individual nodes don't need to be really expensive computers with redundant power supplies and RAID. It's just simple boxes. Google doesn't even bother. Like if one of these big cluster machines that Facebook or Google or Yahoo has a hard drive failure, they just switch the machine off remotely. They don't send a technician to fix it because that's too expensive, right? And now we have a system where lots of computers can process something in parallel using only the data that they have locally, and they don't need to communicate with one another in order to achieve their goal, a share-nothing architecture, which scales really well, because if the computers did have to communicate with each other in order to get their task, the job done, then at some point you'd have a limit to scalability, to the number of nodes in the cluster, right? And the basic flow for a MapReduce program is that you have a mapper reading a record, let's say, I don't know, a line in a text file or something, and it emits key and value pairs. So if you read, let's say, a web server log, you could extract IP address and number of bytes transferred, for instance. And a reducer then receives across all computers, so that's where you have network I/O, across all computers, receives for one key all the values that all the nodes have computed or emitted from their input splits, okay? So And the magic is that the MapReduce implementation, for instance, Hadoop, will, before it does that, aggregate across all the computers, all the values for the same key, and send one process on one machine the values for this one key. So if you have something like this as the stuff map has produced, then it's going to be aggregated like this, and these get sent over the network or locally to one reducer instance and these to the other. And they can do a sum in this case. And now we have the IP address and the number of bytes transferred for that IP address extracted from our logs, right? So roughly in code with a fictional parse Apache log line function, we would emit the IP as the key, the bytes as the value, something like this. In here, the magic happens, the reduce step, before the reduce step is invoked, our MapReduce implementation would do network stuff and grouping and sorting, and then we'd get some sort of result, right? Because we do an array sum, we couldn't do that in real life, because array sum means we need to buffer all the 700 trillion values for that one key that Facebook probably has for one IP address. So you have to do streaming, processing, etc., but that's not the point. This is just to illustrate the basic functionality. And then this is the result, right? And Hadoop does that. Hadoop is also an elephant, which is good for us PHP folks. It's a MapReduce framework, and the cool thing is it allows us to focus writing on mappers and reducers, and works really, really well because all the big boys are using it. For instance, Facebook mostly uses it together with Hive. I'll explain Hive in a moment. The largest cluster holds over 100 petabytes of data. This is serious stuff. It doesn't, like, there's lots of bug reports from all the big folks. It's like, oh, so we now exceeded 10,000 nodes in our cluster, so and now we're getting these issues. So everyone else, like us normal people, are probably fine. The typical node, they have not that much memory per computer because they don't really need that. Lots of disk, obviously, can be cheap disks. If they fail, it's no big deal, because redundancy for storage is implemented in software. Gigabit Ethernet connections and trunk Gigabit Ethernet on the rack level. And they use a feature of Hadoop that's relatively important for things like these. Hadoop is aware of your, it's called data locality and rack awareness. So it knows how your racks are organized. So if you store data in Hadoop, in HDFS, it'll store 2 copies of a block on the same rack, and then a 3rd copy on another rack. Because in case that rack switch fails, the data would be gone, right? You don't want that. But you want another copy of the data locally just in case something bad happens. And you can quickly access it over the rack switch. So it's very optimized. Yahoo also has, they won the TerraSort benchmark, like basically every year. They just go, let's just have 20,000 computers and win just sort a terabyte or even petabyte of data in as quickly time as possible. And they mostly use Pig. We'll look at Pig in a moment, or I'll explain what Pig is in a moment. That's that. A couple other notable users, interesting applications that other people are doing. Twitter. Twitter mostly does analysis in the background, right? A very common thing that you do with Hadoop is any sort of recommenders, any sort of background processing that you then use to figure out information about what's happened in the past, to make recommendations or to deduct actions for the future. For instance, LinkedIn computes their friend suggestions. Last of them, the charts and the you might also like. This is a classic application that doesn't work in real time though, right? So you feed it data. For instance, if you're an online shop, you feed it every click a person has made on products. And then you correlate these clicks with other people who've made clicks, and then you figure out what have these other people actually bought. And then you present these purchased items to the user who's only clicked things but not purchased things, and that's how Amazon recommends things to you. One popular algorithm for this is collaborative filtering. And that actually goes a lot further. You can even do things like, stuff like Yelp or Quip could have recommendations based on your previous based on your previous ratings. So to figure out this is a death metal club. So people who like death metal because they rate other death metal clubs like better, or because they give good ratings to other places that also where people have given the same good ratings, then it'll rate those people's ratings higher for a specific person. That has the so-called cold start problem, obviously. If an anonymous user goes to the site, you know nothing about him, which is a problem. You can then tap into the Facebook graph and everyone will be like, woo, privacy. But you can do it, right? A friend of mine actually runs a company like this. They do exactly that. So you have a sign-in with Facebook and boom, all of a sudden it figures out through what your friends like, etc. It correlates some things and it can give you recommendations. The New York Times did a very interesting thing. They chose that particular approach using Hadoop. It's actually not the best use case for this. But back then, it was the only real distributed processing system available as an open source platform that could handle this scale. They scanned every single page of every issue of their newspaper ever released, and that dates back to 1871 or something. So they had a scan of every page, and then every mapper didn't get lines of text as input, it got one picture of one scanned page. Then used OCR software in the mapper to convert the picture to text and figure out where on the page the columns were, so which parts of the page formed an article together. And they ran that on EC2 ad hoc, cost a couple $1,000, took less than 24 hours, I think. And that's how they converted their entire archive to digital form, and it's now available on NewYorkTimes.com. So I've shown you how the real, on a very basic level, how you write a map and a reducer. So you emit a key, then aggregation magic happens. You can control that a little bit, how it groups keys, etc. And you can do nifty tricks based on the fact that for all the keys it gives you, it will always sort your records by key, right? So you get key A first, then key B, then key Charlie, Delta, etc. And if you then tell Hadoop, well, my key is a tuple of, let's say, 2 entries, but for the purpose of giving everything to the same reducer, I want you to look only at the first part of the tuple. Ignore the second one, right? So if you have A1, A2, A3, A4, those all would go to the same reducer if you tell it to only look at the first part. But it would still sort all 1s first, then all 2s, then all 3s, then all 4s. And you can do really nifty joins with this. Maybe we'll have time to look at that later. But once you start doing this, it gets a bit complicated. And your average business intelligence guy probably can't write these programs, right? So Hadoop has other execution models. Because it's actually, Hadoop is really just a distributed processing system. The most famous application of the thing it became famous for initially is the MapReduce feature it has, right? It's actually a separate project even inside the Hadoop system. You can write MapReduce jobs to achieve some sort of parallel computing. You can also use Hive, I mentioned that earlier, that has an SQL-like syntax. So all you need is your data in tabular form, and Apache logline obviously isn't really tabular, but you could convert it to some sort of comma-separated values format. Or you could take your existing users database and just load it into a Hive table. And that has columns, right? And then you can start joining on that table. Because you really just write an SQL query. You say, select star from purchases, which you've loaded live through some sort of streaming thing live into HDFS. Join user, the thing you're used to, right? And the user database, maybe you copy from your actual MySQL system every night or something like this. And then you do analysis on it. In the background, Hive will analyze your query, maybe sample your data, figure out the best approach of computing the result you want, has a proper query planner, it's really advanced. Facebook, I think, has a dozen people who only spend all their time working on Hive and improving it, which it's an open source project, obviously. And then it produces MapReduce tasks, ships them out to the cluster, and they return at some point. The cool thing is, because it uses an SQL-like syntax, it's obviously really suitable for plugging into existing business intelligence tools. So it has JDBC and ODBC interfaces. So you can have nice pie charts in Crystal reports or something. But it can take an hour, 2 hours, 5 days, it depends on how large your data and complex a query is, for a result to come back. This is not instantaneous, right? Pig is similar, except that you don't write down an SQL query. Instead, you use a language called Pig Latin to explain the steps that you want. So you say, load data from, then you say, aggregate by, join with another loaded data set, order by this and this key. So you describe the steps that you want, and then again, it looks at your data, it has a query plan, it figures out what to do, and then it runs MapReduce jobs for you. So those are both abstractions. If you want to be a bit closer to how you actually program traditionally with MapReduce, you could use cascading. That's an abstraction layer for Java, which takes most of the pain away of dealing with the low-level map and reduce classes inside Hadoop. So that makes your life a lot easier if you compare the examples online of just native Hadoop class MapReduce jobs and cascading jobs. This is more useful, and obviously because it's also a JVM-based language, scalding is basically cascading for Scala, which is even easier to write with. And so that's your options for running your own stuff, right? Or you could use completely different approaches, completely different systems. Mahout is basically a collection of machine learning algorithms. So the collaborative filtering algorithm I mentioned earlier, you just throw a bunch of comma-separated value files at it with defined columns, and it'll figure out some sort of correlation for you, and there's your recommendation. So it's really easy. Like, all you need to do really with the out-of-the-box algorithms is get your input data into the right format and let it run every hour or every night or something. HBase, who has heard of HBase? That's a lot of people. No? Really? So, who's heard of Bigtable? Okay, some more. So HBase is Bigtable, right? People always describe it as a table with many columns, like billions of columns, and then columns of variants and versions. And that's really that's an Excel user's look at things. What it really is a document database, basically, right? But it has a very interesting twist. It runs on top of Hadoop infrastructure. It stores its information in Hadoop's distributed file system, so it has all these redundancy features and durability features. But you can query it, well, really, really quickly, like sub-millisecond performance is what you get out of it. But you can't say, give me all the rows where some of the fields contains these and these values. All you can do is say, give me this key, or give me this range of keys. That's it. Similar to Cassandra. Who's heard of Cassandra? Similar thing. Cassandra is like a ring topology, but it's a bit different, but similar, okay? So if you have HBase, HBase is really useful, for instance, to just to store series of events, series of postings. A good example is Tumblr. Who's used Tumblr before? Okay, so in Tumblr, but you guys know what Tumblr is, right? Yes, everybody? As a blog system? Cool. So there's one special way about Tumblr of consuming information. You have a so-called dashboard. So instead of subscribing to 50 RSS feeds, you go to your dashboard, and all the blogs you're following have all their feeds mashed together. It's like a Facebook feed, right? And for a very long time, I think until last year some point, they used to just query ad hoc query MySQL databases. And that would always go down. That's why the dashboard was slow and would always go down. Because they would look at, okay, so you have 400 friends. These 400 friends store their posts in different MySQL databases, so we'll query all those now. And then we'll get all the results, and then we'll order them by time and display them. That's not very efficient. So they converted everything to HBase. This is what Facebook does as well for their feed. Who knows what happens when I write a post on Facebook? On a storage level? Louder? Or maybe nothing happens because I have no friends, but no. So, if you write a new post on Facebook, it doesn't get stored in a database and then it is retrieved whenever one of your friends looks at their feed, right? When I write a new posting on Facebook, it gets written to all my friends' feeds. it gets copied. If I have 500 friends, 500 copies of my posting are made. Because that's on the scale they're operating in, that's a lot faster to query. So storing that in HBase would mean basically you use a key like user ID dash timestamp. That's all. So for 500 friends, 500 times the same entry, 500 times the friend's user ID dash a timestamp. And then if you click new latest stories, it'll just go to HBase and say, give me all keys between my user ID dash current timestamp and my user ID dash 5 years ago. And it'll take the top 20 results and display them to me. That's how it works. There's no other way to do it on their scale, right? So as you can see, if you do big data, sometimes you need to think differently. Sometimes you need to accept the fact that you do need redundant storage. You do need to duplicate data, and always remember, storage is cheap. You always want to keep everything around forever. You don't need to optimize for bytes, because probably even on SSDs, it's a lot cheaper to store the data than to be angry later because you don't have it anymore. Nudge is a search engine. It's actually a web crawler, so if you want to launch your own Google on top of nice infrastructure, go ahead. I was just adding it here for completeness' sake. There's a new cool kid on the block that I'll go into more detail in a moment on. It's called Impala. Impala solves the problem of this latency that you have when you submit a MapReduce job. If you do a Hive query, 2 minutes, are spent on optimizing the query, figuring out what happens, sampling the data, then it assembles a bunch of MapReduce jobs. You have a bunch of seconds overhead at least, which gets shipped out to the cluster, and an hour later you have your response. Impala potentially gives you an instantaneous result. It doesn't use MapReduce, but it uses Hadoop's distributed features. So that's going to be really interesting, and we'll look at that in Chapter 2, Real-Time Big Data. For most of us, I've said this earlier, I think the Hadoop part is a lot more interesting. It's also easy to get started with. That's why I will do a demo on Hadoop, not on the other technologies in a moment. Because sometimes you want to figure out, well, how has our order history changed? You want to send reports every morning on click activity, etc. You can do that in the background. That's not time critical, right? But sometimes you have tasks where you cannot wait for a few hours. Good examples would be anything that's security related. You want to detect intrusions, figure out fraud on an online shop, or another good example, Twitter's trending topics. They can't compute those every half hour. They need to do it on the fly, right? Because if some election thing, some Israel-Gaza thing, whatever is trending, you want that up within 10 seconds, right? So people can figure out what's going on. That's Twitter's premise, that you're basically following the world in real time and what is everybody in the world talking about. So for these kind of systems, batch processing is really not going to cut it. So we need something better. We'll do it live. Twitter figured out that problem, and they came up with a technology. Actually, they didn't write that themselves. They purchased a company whose name escapes me at the moment. They bought this company, and this company had a product called Storm that Twitter then open sourced. It's pretty well developed now and pretty active. It's often called the Hadoop for real time. The basic architecture is similar to Hadoop in that it has a central service similar to Hadoop's job tracker that knows the job you want to run, and it knows what other nodes are in the network, and it'll send information out to them in order to give them instructions on what to do and control the basic flow through the system. But other than that, the way it operates is obviously very different, because in Hadoop, you say, I have these files, do something with these files using this task, right? This job that I wrote. Whereas in Storm, you have a central process coordinating everything that runs so-called topologies. Because if you are Twitter, you have a never-ending stream of tweets. A topology never stops, right? It always keeps ingesting data, does something with it, passes it on to the next step that does something with it, maybe counts the number of tweets per hashtag, for instance. And that's continuous processing. For these continuous processors in a so-called topology, they consist of two parts usually, and then you have many of these parts assembled together, is a so-called spout that produces a stream. So it, for instance, receives a hashtag, a full tweet on Twitter, and from that it produces tuples of information. For instance, a hashtag and a count or something, or a time, right? For all the hashtags in the specific tweet. And then that gets passed on to a so-called bolt, and the bolt then would, for instance, take the hashtag and increase the number for that hashtag in the internal counter, and output it again. And then you could do the next step, next step, next step. That's how you chain them together, and that works in real time. It doesn't have a good persistent storage system, because that's not really interesting to Twitter. Actually, it has a bunch of reliability guarantees that even for Twitter don't really matter in most cases. One interesting aspect for us PHP developers is that you can write these bolts, not the sources, but the bolts in other languages. It uses standard in, standard out, and JSON to communicate, so you can write one in Python or PHP. So it receives a JSON on standard in, your PHP application figures something out and writes a JSON to standard out. And that's how you can implement that in your own system. Probably using PHP as a runtime is going to be the bottleneck in that case, and not your network I/O. But hey, for prototyping, might be fun. And so this is what I just meant. It's probably not even relevant for Twitter. It can actually guarantee transactions. So it can guarantee that something got counted, for instance. And it also can guarantee processing of messages. So you can say, well, I want this counted and only once. And I want to guarantee that, a call only ever returns if this thing has been processed successfully, which for some applications probably matters. Like in the fraud detection case, you want exactly this behavior. And similar to how Hadoop, as you've seen, allows other use cases. For instance, you can build a distributed big table NoSQL database on top of Hadoop that doesn't even use MapReduce, but it uses the underlying distributed mechanisms like HBase. You can do other things on top of Storm. People are slowly starting to build other applications on top of Storm. One interesting aspect that you, as a developer, can tap into is distributed RPC. So basically, you make an RPC call to the Nimbus, or a service provided by the Nimbus, and that'll, through topologies then, well, without topologies that you have to write yourselves, basically send RPC calls to many, many backend instances. So it's maybe a Gearman replay, no, not really, but something similar. So if you ever need to do massive distributed computations, this might be it. This could be something that the New York Times could have used had Storm existed back then to do their scan to text conversion. And the other candidate here is Impala. I mentioned that earlier. Anybody heard of Dremel recently? Dremel is, there is a Google service now available called BigQuery that's allegedly based on Dremel. Dremel is Google's new MapReduce replacement, because they figured out, well, computing our search index using something like MapReduce with the overhead it has and with the batch-oriented workflows it provides can be difficult, for, again, trending searches, etc. They want a more real-time approach. So they wrote Dremel, which is essentially basically SQL queries that run in parallel across many boxes. And Impala does exactly this. It's built on Hadoop's version 2 infrastructure. So Hadoop version 1 was very focused on the whole MapReduce aspect. So it basically had the distributed file system and the MapReduce implementation tightly coupled, and you couldn't use the whole scheduling and coordination aspect without the MapReduce aspect. So they fixed that for version 2 with a so-called Yarn system. And now all of a sudden, it's actually a general purpose distributed computing platform. And one of the first prominent applications is Cloudera Impala, which I think it got released or announced 2 weeks ago. There's a beta out now. Cloudera is one of the companies that provide commercial support and commercial distributions for Hadoop. Others are MapR, IBM does it, Yahoo took all their their Hadoop knowledge and all their engineers and founded a new company called Hortonworks. So there's a bunch of big competitors now on the whole Hadoop market that can give you commercial support if you want it. But they all open source their distributions as well. And they're actually really good. So these guys, for instance, release, I think every quarter, a distribution called Cloudera Distribution for Hadoop, CDH, where they backport patches and test for stability. So instead of using the maybe unstable and not well-tested and hard to install native Apache Hadoop, you just download one of their packages, works, done. So that thing doesn't use MapReduce, and it doesn't have the job setup overhead, right? In that regard, it's similar to Storm. The difference is that you can query existing data in HDFS or HBase. Obviously, if you want to query stuff in HDFS, then you need to write it to HDFS first, so there's a bit of delay. But if you want proper real-time stuff, you can probably get away with just quickly writing it to HBase, because HBase can give you hundreds of thousands of writes per second if you have a large enough cluster. And then query that instantaneously. And the cool thing about this project is that it has an interface that's completely compatible to Hive. So if you have an application that already works with Hive, you can just say, well, okay, I'll just use a different query engine, and instead of a query taking 2 hours, it finishes in 5 seconds. So with the right amount of query and with the right set of data, you can get query response times from this system that are suitable for using in applications, which makes it interesting, because all of a sudden you don't have to compute weird indexes of recommendations in the background. You can do stuff on the fly. You can tap into your terabytes of big data live, right, and show it on your website or use it for other purposes. And this performance characteristic of Impala makes it really a potential game changer. It's very new. Nobody has really played with it yet, including me. I hope I'll find a free weekend soon. But that could be really, really, really cool. And the obvious advantage of it is that it runs on top of your existing infrastructure, right? Storm is interesting if you absolutely do need the super live behavior, but you need to duplicate a lot of infrastructure. You need to duplicate redundancies, etc. This just works on the top of your existing Hadoop cluster. And the Hadoop cluster really just needs redundancy and expensive hardware for the so-called name node that knows where everything in a system, where all your data lives, right? The file allocation table of your distributed file system. For that, you need 2 boxes, ideally, with redundant power supplies and RAID. All the other nodes can be cheap hardware, like just something you buy in a store and just put in a shelf. And this could work on the same infrastructure, so that makes it very interesting. I'm going to demo Hadoop now using the streaming interface, so we'll probably just look at some Apache logs and figure something out. We're going to do streaming using PHP, so we don't want to write Java mappers and reducers, right? It's a PHP conference. There's a little toolkit called Hadoop PHP that helps you writing mappers and reduce jobs in PHP. Hadoop streaming works exactly the same as Storm streaming. So it uses standard in and standard out to communicate with your process. And this takes care of all this. It knows the input splitting, the formats, the line separators, etc. So you can focus on writing your job, and then it packages a file archive for you and a shell script. That was written by this guy, you might know him, and we can look at this now. I wrote this long ago, so if anybody has any kind of pull requests to send me, feel free to. So I have Hadoop here, and because the future doesn't belong to the faint-hearted, we should set it up from scratch. Boom. Delete my data as well. I have it here somewhere. Yeah. Cool. So, extract. I'm going to use the older version right now because I have the environment variable set up for this. go there. There's a configuration folder. And in the configuration folder, we just need to adjust 3 files. Here, we need to tell Hadoop, is it this one? No. This one? Yes. No. Yes. So we need to tell it where to listen for where the name, on what address the name node should listen, that thing that knows where every block lives of data, and it needs a directory to store stuff. Then for HDFS itself, we want to tell it to only store 1 replica, because by default it stores 3 replicas for every block, and I don't have 3 laptops here, just 1. And the job tracker that coordinates all job processing, in newer versions of Hadoop, this is called the application master and stuff. It's slightly different from the setup process, but not too dissimilar. So we've done that. Now we need to format our file system. Name node formatted, and we can start all daemons. Okay. Okay. Stop here. Good. That looks okay. So we have a MapReduce cluster using 1 node, and we have 1 live node in the system, some capacity available. There is nothing in the file system. So we should put some data in. There we go. I have some stuff here, access logs. That's around 400 megabytes of access logs from 2003. So that's older. That's some of you might have not been on the internet back then. So back then, the coolest thing in 2003, for a while, for a few days, was the Star Wars kid. Essentially a kid jumping around in front of the camera with a lightsaber. And the guy hosting this video file, he made the access logs from those days available, and we want to import those into Hadoop right now. So we want to, with the distributed file system, put access logs to /access logs. And now we can see if they exist. There is no home directory, but it's in /. So as you can see, I put gzip files in there. And Hadoop HDFS has a really cool feature called transparent compression and decompression. So we can look at one of those files. You can minus cat. You don't want to do that on binary files because your shell will take 2 days of beeping. We want text output on access logs, access log af.gz. And if I could type properly, where's me typo? Yeah. There we go. So that's an Apache access log, right? Now we want to compute some, yeah, okay. So this Hadoop PHP thing comes with a bunch of examples. One of them is hits by URI, which has a mapper implementation. The mapper parses an Apache log line and emits the URI as the key, and the number 1, because it's 1 hit to that URL, as the value, right? And this is just some counting, blah, 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 blah. And then the reducer receives a traversable of the values. I told you earlier we don't want 500 million integers, 1 buffered in our RAM because we run out of memory. So we just for each over this and sum it up, right? We could use iterate apply maybe, but it's, nah. So we can compile this. We just give it the folder, compile it here, change mod. And then we can run this. It tells us to give us an HDFS input path, / access logs. Sorry, you should have said something. This is better, right? Yes. You guys are too shy. Has anybody told you this? Access logs, and we'll give it hits by URI as output path, right? It'll create this for us. Let's see if that works. Yeah. We have a tracking URI. We could click there through our web interface, or we just look there directly. So we have a map introduced, job running for 7 seconds. Job setup was successful, which is good. There is no errors. There's some counters. I don't know what those mean. Okay. Good. And the map is running. We've written quite a bit of stuff already. There is nothing in the error logs, I hope. Nope. Nothing bad, anyway. So we have a bit of statistics here. Well, we've spent 10 seconds, obviously. So we've read quite a few bytes already and written quite a few bytes. We've written 70 megabytes to disk already. Java is using 400 megabytes of memory. And as you can see, even though it's not finished mapping yet, it starts reducing. That shouldn't be possible, right? Because maybe in the other half of the reducers, of the map inputs, because we're running 4 map jobs, I think, there could be other values for the same key. It's not actually calling the reducer process in this case. It's just it starts sorting values from finished output. So it's just preparing things. And there's the reducer. It's running. We can also see the process here. The progress here. And that's going to be a bit slow now. Because what it does is, it now takes a URL and a 1, and a URL and a 1, and a URL and a 1, and hundreds of thousands of those, and moves them locally, buffers them on disk, puts them into memory, etc., etc. So this is a laptop. It's not very fast. The disk is not the fastest. And obviously, it's a bit inefficient because we are just, copying ones and ones and ones and ones for the same key over the local network. So we can optimize that in this particular case, because we're just counting something. So instead of saying we transfer hundreds of thousands of ones and using the same URL to one reducer instance, we can already, just using the output one mapper produced, go over all the same values, right? And already count them. So instead of sending 500 times the same URI and the 1, we can send the 1 URI and number 500, right? So in this particular case, it doesn't matter that much, but once you do it over the network, instead of sending a couple of megabytes or even more over the network, you send just a couple of bytes from one mapper to one reducer instance. So that cuts down on network I/O. And we now took 2 minutes and 13 seconds to do this. We can look at the output real quick before we run out of time. So there's one part, because we had one reducer instance, and we can look at the text output. So that's obviously some sort of, well, there's many bot attempts and stuff, and small, oh, here, this seems to be a popular URL, 223,000 hits, right? So we had 223,000 instances of this URL, tab 1, new line, buffered on the disk, sent across the network. We can optimize this using a so-called combiner. So instead of sending this 223,000 times, we just send it once, right, to the reducer. To do that, we tell it to use an internal reducer because that's more efficient. We don't use PHP now, but Java, and we use a combiner. And the combiner does exactly this. It batches everything up before it sends it over the network. And our mapper needs to be changed slightly to not emit just the request URI, but the instruction we want to give this aggregate package with the combiner feature. We tell it, make a long value sum, and try again. So, where's me terminal? There we go. So compile this. Hits by URI2, new output folder, and run it again. There's a new tracking URL. That's running now. and that should finish a lot faster. What I could do now is ask one of you for your laptop and an Ethernet cable, set up Hadoop in a similar fashion. In the config file, also, well, just change the IP addresses of the name node, right? So it connects to this machine. We could run the same thing again. The distributed file system, I would have to set it to 2 replicas, right? So it's on both computers. If we then run the job again, it's almost twice as fast, minus a little bit of setup overhead. It really scales linearly with the amount of with the number of computers you have in your job, in your cluster. So 2 minutes and 13 seconds, 47, 48. Almost done. See, that's a lot quicker. The reducing is a lot quicker because it doesn't have to consume. The reducing ran over 4 million records, I think. Reduce input over 2 million records, and now it had a lot, 2 million combined input records, and reduce input records were just 10,000. So instead of processing 2 million, we processed just 10,000 input splits, right? So the whole thing finished in 1 minute and 12 seconds, so it's almost twice as fast, just with this little optimization. Back to presentation. That's me. Okay. Things to keep in mind. One thing I haven't discussed yet is data acquisition. You have a myriad of options. You can use syslog and then, collect whatever you have in syslog, batch it up every 5 minutes and send it to HDFS or whatever stream processing you have. These stream processing solutions, like Storm, also have their own interfaces to send live data to. For batch loading, really, what people use is some sort of cron to send Apache log files or output from syslog into HDFS. That's one alternative. Another would be if you have an existing SQL database that you want in for querying in Hive, you would use a utility called Scoop that does that for you. It syncs data both ways if you want. So if you produce some output with Hive, you can write that to a table and then have it back in your MySQL. That's a popular application you do often with systems like Hadoop. You compute something every hour or once a day, and the result gets written back to a MongoDB, a CouchDB, a MySQL, where you can query it quickly, right? Or if you have streaming, so if you want streaming solutions, you shouldn't use Facebook Scribe. In case you've heard of it, forget it. It's really a mess and unstable. Better alternative would be Apache Flume. It's a system where you can say, my data starts here, and I want it there, and there, and there, and here's an aggregation, and here is a transformation, and please annotate it here, right? And that's really powerful, because then you can say, I send information from my PHP application to this Flume listener, and it'll write it to HDFS, it'll write it to local disk, and it send it to Storm or something, and really critical events will also be sent out via email. It's really powerful. Similar systems, Apache Chokwa and Apache Kafka. Kafka works really, really well with Storm. They're almost like soulmates, if you will. Very good integration. If you want to keep it simple initially, and you say, I don't want all this Hadoop stuff, maybe take some inspiration from Etsy. Etsy is an online shop, a really big one in the US that's scaling massively. And they have written a system called statsd. It's a Node.js process. You just use simple UDP sockets to send it information, and it'll batch this up. Like this is their PHP lib. Where's my pointing laser? Out of battery? Oh, no, there we go. Dual lasers. So you increment the value, for instance, right? Like here. And it'll occasionally batch those up and flush them out to Graphite. Graphite is a visualization and storage library where you can have nice graphs, right? The problem with this approach is that you need to know what you want to know. If you're not logging, if you don't have these calls, you never know the data. So that's one important thing about big data. Whatever you can log, log it. Even if you don't use it. Log it to local disk, write it to tape, so you can later put it into your HDFS or something once you have a Hadoop cluster. Please do it. You'll be really, really glad you did. Every click, every purchase, every cancel problem, every error, you can use it later. So this information is what gives you power, and you should store it. And that's where HDFS is so powerful. Storm can't store this stuff forever for you. It can analyze in real time, but you also want archival, and that's where HDFS and Hadoop shines. If you want to, for operations, like classic monitoring things, you can combine all these technologies. So you can, because Flume and Choco have really sources for everything. You can measure kernel I/O, FastAGI stats, etc. And many people now build flows into HDFS store for persistence, then use Impala queries and correlate them with Storm results. And then they use cloud services for notifications. No, just kidding. That's bullshit. Just use Nagios for this. But that's easier. That's what it's made for, right? So these utilities still have a place, especially if you just want to monitor your servers and your applications. These things still shine. Isinga obviously is just a Nagios with a nicer interface. That would conclude this presentation. We're out of time. There's no time for questions. Thank you.